To explain how we canonically implement a finite state machine in Verilog given a state diagram, I've drawn this random state diagram here. We can see it's a valid state diagram because every state has got a red and a blue arrow coming out. That's my color scheme for blue is a 1 and red is a 0. And of course that's telling us what the input is. We take this transition according to what the input is. So if we're in state A and the input's a 0, then at the next rising edge of the clock we move to state B. Otherwise, if at the rising edge of the clock the input's a 1, we move to state C. So it's a valid diagram because every state has got one red arrow going out and one blue arrow going out. Let's move this to the side so that we can start to implement our Verilog code. We start by giving our module a name, my finite state machine, and then the input, we need the clock. The input we see is just 1 bit. Those are the red and blue lines and they're labelled with just 1 bit. So the input I can call in. The output looks to be 2 bits output, and it depends how we're going to define our output logic, but this time I'm going to use a case statement, so I know I need a register, so output register 2 bits for my output. The first thing we can do is do our parameter definition, or in fact I should say define state representation. That's a more accurate description. And we use local param, so a local parameter, not one that can be modified. And this allows us to change from letters into states. So when we're in state A, you can't represent A in a finite state machine, so you need to use a number. We've got 3 states, so we need at least 2 flip-flops to remember both of them. We can do it using 3 flip-flops if we want to, but we'll just use 2 flip-flops for now. So somewhat arbitrarily, I can say that the first state will be stored as a 00 in my flip-flops. The second state will be stored as a 01, and the third state will be stored as a 10 for argument's sake. Now, for this very particular finite state machine which I drew at random, because we need 2 flip-flops to represent the state, and because the output is also 2 bits, and because the output is different in all these 3 states, I could have actually used a state representation where state A was given by 10, state B was given by 01, and state C was given by 11, and that would mean my output logic is trivial. The output is just the current state. But because I'm showing you a general procedure for how to do this, normally that will not be the case, and we do it this way instead. Exactly how to choose the state representation is a bit of an art, and we're going to discuss that a bit later in this lecture. For now, all we need to do are label our states, and then we can give them numerical numbers 1, 2, 3 up to however many states we have. That will always work. If you change the representation, you can change the efficiency of the design. That's a topic for a bit later, but it will always work if you just label your states and number them 0, 1, 2, 3, 4 until you've labelled all your states. Continuing on, we need a semicolon there. Now we need to define our variables to hold the state. So state and next state. I'll call them variables even though they're nets in Verilog, but call them variables. Register, so we decided we needed 2 bits to store our state. I can just call it state. Normally, when you design a finite state machine, the states have got some meaning, and you can perhaps give the state variable a more meaningful name as well. And how are we going to define our next state? Well, I'm going to use a case statement in this case, so I need a register here, and I will have next state down here. Now, rule number 1, always initialize our state. So what's our starting state? It wasn't labelled. That's a mistake in the whoever drew the state diagram forgot to label the starting state. Let's assume we start in state A. So we've got state and next variables and initialization, which I'll add here, and initialization. We now need to have our flip-flops always at posEdge clock. State becomes, after an infinitesimal delay, the calculated next state. Now we can have our next state logic. Given the state we're in and given the current input, what will our next state be? So often, not always, but often, it's convenient to use a case statement for defining this. And indeed, we're just defining combinational logic, and combinational logic can always be defined using a case statement because we're basically just specifying the truth table. Now, of course, if it's a very big finite state machine, then a case statement might be too cumbersome, too many lines there, but in this case, we're fine. So case, and our next state depends on both the input and the current state. So I can have input and the current state in here, concatenate them together. And now I just go through the different combinations. For other problems, it's probably going to be too cumbersome to have a case statement with both in and state in there. Then your case statement might just depend on the state, for example, and within each state you switch depending on the input. In fact, I'll show you how to do that after we've done it this way first. For the different cases, we are concatenating in with state, and because we want to use our letters A, B, C for the state, then I need to use the concatenation operator. And when you use the concatenation operator, it's very important you select the correct number of bits, otherwise things won't line up. So if my input is 0 and if my state is A, then what will my next state be? Remember, we're defining next state logic, so all we want to do is make an assignment to next state. Now remember, we're not going to immediately move to next state. We move to next state at the next rising edge, because that's what our flip-flops are doing, waiting for the next rising edge to transfer next state into state. Okay, so what we do depends on our state diagram here. So we're in state A and the input 0. Where do we go? We're in state A, the input 0, we go to state B. So that's easy. We just come over here and put a big B right there. Move on to the next case. If the input is a 1 and we're in state A, then where do we go? From our diagram, we go to state C. And then we repeat this 4 more times. If the input's 0 and we're in state B, where do we go? We look at our diagram, we find state B, we have a look at so 0 is red, we look at the red arrow coming out. The red arrow coming out of state B takes us to state C. If, however, the input were a 1 and we were in state B, then we look at the blue arrow and we see that the blue arrow takes us from B to A. If the input is a 0 and we're in state C, so in state C, the red arrow going out takes us to state B. And if there's a 1 at the input, it means we follow the blue arrow from C. If we take the blue path, then we end up in state A. And then before we end anything, what happens if cosmic rays hit our flip-flops and knock them around? We might end up in an invalid state, and then we need to work out what to do if we end up in an invalid state. You could halt the machine, you could flash a light, you could do something, but for us, we'll just return it to the initial state. And we decided the initial state was A, so next state equals A. End case. And we finished the next state logic. This is entirely valid, but I'm going to show you a second way of doing it. The second way of doing it is to just switch on the state, and you'll see why in a second. It does make things a bit nicer in this particular instance. In other cases, you can use a case said statement and have a smaller number of lines as well. So there's more than one way of skinning a cat, as they say. Here's a second way. So now we just have to switch on the 3 different states that we're in. We don't need these 3 lines here. Delete those. And over here we use inline if statements. So on the right hand side I now test in. So this first line says if I'm in state A and the input is a 1, where do I go to? So I'm in A, I follow the blue path, I go to C. Now I'm in state A, if the input is 0, where do I go? I follow the red path and I go to B. So the first line's now correct. Second line, I'm in state B, if the input is a 1, because remember 0 is false, true is 1. So if I'm in state B and the input is a 1, I go to state A. Otherwise, if I'm in state B and the input is a 0, I follow the red thing to C. Finally, if I'm in state C, I test the input. If the input is true, i.e. if the input is a 1, I'm in C, I get a 1, the blue arrow takes me to A. Otherwise, I'm in C, I get a 0, the red arrow takes me to B. And so this, for this particular example, is probably the nicest way of implementing it using a case statement. Moving on to the output logic. Then we're going to do the same thing with a case statement. So we're going to need an always at star and then a case statement. And simply because I'm running out of room, I'm going to jump over here. So case. And again, we're going to switch on state because it's a more finite state machine. We know that from the state diagram because the output's given to us in the same circle as the state name. So the output depends only on the state. So there must be combinational logic depending only on the state that tells us where to go. And the same thing, if I'm in state A, then the output is going to be equal to 1, 0. If I'm in state B, the output's going to be equal to 0, 1. And if I'm in state C, the output's going to be equal to 1, 1. End case, end module. And we're done. To summarize, given a state diagram, which is correctly labeled with the starting node, start, we can almost immediately implement it using this canonical structure for a finite state machine. And even if we implement our finite state machine some other way, not via a state diagram, but via some algorithm or something, we still want to follow this canonical form. The only exception might be we don't need names for the states if there's some algorithm involved, such as if we're using a counter or a timer, where our state's going to be an actual number and we're going to add or subtract numbers to the state. Otherwise, if the state's got names, like in this example here, A, B, and C, the first thing we do after having defined our inputs and outputs and clock is define our state representation. Here we do have a choice, but in the absence of anything better to do, and we'll discuss that later, you simply count how many states you have, work out how many bits you need in order to store that many states, and then label the states 0, 1, 2 until you've labeled all your states. So here we go, state A is 0, state B is 1, state C is 2. Next, we define our variables for holding the state and the next state. The state's always going to be a register. The next state will be a register if you use a case statement. It will be a wire if you use an assign statement. Make sure to initialize your state to the starting state when you declare your state variable. Next, we define our flip-flops. At the rising edge of the clock, the next state becomes the current state. And finally, we just have to define 2 combinational logic circuits. The first one tells us what our next state is given our current state and the current input, and the output logic tells us what our output is given the current state, because it's a more finite state machine. For our next state logic, it will always work to use a case statement. It's up to you whether you want to switch depending on both the input and the state, or just the state. In this case, because the input's only 1 bit, it's nicer to switch on just the state. So we've got case state, and we just go through all the possible states. And the interpretation is relatively straightforward. If we're in state A, where do we move to next? Well, that depends on the input. If we're in state A and the input is a 1, we go to C. If we're in state A and the input's a 0, we go to B. And we correspondingly work out where to go if we're in states B and C. Always include a default statement, and normally the default action is simply to return to the initial state. That's the next state logic. The output logic, same principle. Depending on what our state is, determines what our output is going to be. Always follow this structure. It lets Quartus know that you're implementing a finite state machine. That means Quartus will display it nicely for you in the finite state machine viewer, and that allows you to actually change state representation without changing your code. It also allows for better optimization by Quartus when it comes to implementing your finite state machine. If you write it this way, then what you've done will be clear and easily understandable by other people that read your code, which is important in an organization where other people might have to help look after your code once you've moved on, for example. And of course, you too, after a year, if you come back to your code, you want to be able to understand what you did quite easily. You don't want to be figuring out all the little tricks you played in there. It's written this way. It's also easier for a human to work out how it's going to be implemented in hardware. And when you're doing hardware design, that's always a good thing. Remember, it's very easy to write Verilog code that produces a massive amount of hardware and inefficient design. This way, we can understand what the hardware implementation is going to be. And lastly, by having this standard procedure to follow, it's much less likely you're going to make a mistake. Once you've done this a few times, you can almost do this in your sleep. There's just a simple standard procedure from going from here to code like this.